Thank you, everyone. Good afternoon, everyone. Uh, my name is Ananto. I would like to share about my own experience as well as a couple of best practices in order to do sizing and configurations for MySQL to achieve higher performance and stability. So bear in mind that we are not going to discuss about how to maintain MySQL performance for day 2. So discussion is only for day 1 only. How to prepare MySQL servers if somebody comes to you and then asking to size up the MySQLs as well as to plan MySQL servers for productions. So this is the content that I would like to cover, which is database server size and configuration. Secondly is a quick optimization on MySQL InnoDB cluster. So standalone, and then after that, clustering HA using InnoDB clusters. And then we are going to talk about MySQL Enterprise features for performance and scalability as well. So what it takes to have MySQL performance and stability? Usually a general requirement is basically for us to understand about workload characteristic. What kind of workload that's going to use MySQL? Is it going to be OLTP? Is it going to be like, OLTP plus reporting? Okay. What is the percentage between read and write and so on? So secondly, we need to do a server sizing and storage capacity as well. And then database server configuration setting and tuning. Okay, we need to prepare. So it is very important, okay, server size and storage capacity, because normally on-prem, we need to prepare the hardware. Once we have buying the hardware or set up the hardware, is the upper limit of where the MySQL can go, right? Because we cannot, easily change the infrastructure. And fourth is database schema optimization and query tuning. Okay, this is actually for day 2. Yeah. Okay, once database is running, once application is running, then after 1 year, after 30 days maybe, okay, we understand which query need to be fine-tuned further, or maybe by introducing indexing. But the effect of this indexing to the query performance as well as the MySQL stability will be a lot. And last but not least is MySQL version and additions. It's very important. Okay, so the goal for this is basically to have faster performance and stability. Consists of operation and optimization of the CPU, okay, CPU utilization, okay, optimize the memory usage allocations, optimize the I/O operation, query plan optimization, as well as getting the performance scalability. Database server size and configuration. First of all, so we need to recognize the potential system bottleneck in our system. So any database application eventually hits hardware limit. So hardware is the limit, right? So the component that we know, okay, since MySQL is installed on the hardware, okay, then we need to deal with this I/O, CPU, and memory as well. Okay, for this I/O, we need to check the seek time and this I/O read and write. Seek time is actually amount of time it takes for hard disk controller to find out a particular piece of data that's stored in the hard disk. And then usually in MySQL database server, okay, we have couple of hard disks that we can club together into a single LAN, so that the data will have spread across, okay, for having more read-write head. So secondly is this I/O read and write when the disk is in the correct position. Okay? And we need to have a speed, okay, to fetch that data for that in that particular locations to the memory. Second is CPU cycle. CPU cycle is related to how the data is in memory, okay, and then get that data and then put into the CPU cache, okay, and CPU cycle is very related to the this I/O as well. Okay, and then memory size. Yeah, if the memory is too small, and data processing is big, then CPU cycle will take long. And last but not least is memory bandwidth. Okay, and when CPU needs data cache, more data that can fit in the CPU cache. Okay, main memory bandwidth become so-called a bottleneck. So we need to understand about our workload. Okay, there are so many options related to this I/O. Okay, and that type of disk. Okay, we can use SSD, for example. Okay, it can deliver seek time between 0.08 millisecond to 0.16 millisecond and throughput around 500 megabyte per second. Okay, and then, or maybe if you want to have like, faster this, then maybe we can think to implement NVMe, which can deliver 6 times around 0.02 millisecond and throughput around 3 gigabyte per second. As we know that MySQL has so-called system variable related to durability. In order to get maximum durability, any data that committed in MySQL, it needs to flush immediately to the disk. Okay, there are two processes basically: flushing redo logs to redo log files and flushing bin log to bin log files. So in order to achieve this, we have InnoDB flush log at TRX commit equal to 1 and sync bin log equal to 1. So sometimes if you try to actually compare, okay, to disable these system variables, let's say we set InnoDB flush log at TRX commit equal to 0 and sync bin log equal to 0 or something higher, okay, to defer the flushing of the binary logs, yeah, then we can see that our database that normally can, achieve 800 transactions per second, it can be like, 9,000 transactions per second or 20,000 transactions per second, okay? But with compromised durability. So in order to get a maximum durability, but also achieve high performance, maybe it is good if we actually move the redo logs, move the redo logs as well as the bin log to the faster disk. Let's say NVMe, by changing parameter like say InnoDB log group home dir, or if we use InnoDB redo log archiving, then we can use InnoDB redo log archive dirs also to store the archive redo logs to the faster disk. And then maybe it is good also if we set the bin log row image equal to minimal. Okay, so that not the entire columns data within one record that getting updated will be flushed into the disk. And then InnoDB checksum algorithm, this is very, very small impact to the performance, but if you are really, let's say having, so-called, want to have a meticulous setup, maybe you can set InnoDB checksum algorithm from normal CRC32 to strike CRC32. So that when MySQL wants to update the data or insert the data into the data file, then it won't check anymore what checksum algorithm need to use. It will straight away using CRC32. And then we need to also configure InnoDB redo log capacity, okay, to something higher, especially for if we have high volume of transaction. Let's say we can set by default is, not by default, okay, you can choose, but best practice is 0.56 times RAM size and divide by 2. Because InnoDB redo log capacity is very, very important, especially if you have a high volume of transaction. We know that the redo log is always like doing round robin, right? So by creating a lot of redo logs and then have sufficient redo log file size, then we can have like, high volume of transaction happening in database. And then if we have this with high I/O capacity, okay, just now my colleague Sumi, this morning my colleague Sumi is already mentioned that InnoDB I/O capacity in 8.4, it will about 10,000, yeah, 10,000. And then InnoDB I/O capacity max about 20,000 or 2 times of InnoDB I/O capacity. But if you have MySQL lower than version 8.4, then it will set to 200. 200 is just a SAS disk, single SAS disk. And InnoDB I/O capacity is actually, give the upper limit for the InnoDB to have the, I/O transaction. So that's why, okay, for this InnoDB I/O capacity and InnoDB I/O capacity max, we need to set same as I/O per second that we have on this storage. Another important I/O optimization on Linux OS, let's say if you have MySQL running on Linux OS, okay, we need to check the I/O scheduler. Okay, there are a couple of I/O schedulers, but MySQL, best practice, to set the I/O scheduler on Linux, either the deadline or none. Okay, both deadline and none is a FIFO, yeah, first in, first out. No scheduling except for deadline. It will prefer to have read first compared to write. So this is sorted based on that. Okay, if you set to none, then it is unsorted. It's completely FIFO. And then VM swappiness. Okay, VM swappiness controls how aggressive is Linux doing a swapping between memory and system disk. And then the best practice is to set VM.swappiness in the kernel setup equal to 1. It is recommended. And then the other one is fstab, okay, the mode where we mount the MySQL disk. Okay, expected, okay, best is to change the default option to no barrier, no uptime, no direct time. But please consult with your OS as well. Sometimes, okay, you know, those variables or those parameters will not be compatible with the latest OS. Let's say, for example, no barrier. Don't put no barrier in Red Hat 8, okay? Or otherwise, when you restart, your database LAN will gone, okay? So, no attempt and no attempt will disable the updating access time for both files and directory while, you know, when MySQL is accessing the database data file. So it will speed up the I/O process. Other optimization on Linux OS, okay, we have, internally we have, I mean, is published, okay, in our Oracle support, okay, document ID 2733.424.1, okay, recommended Linux kernel parameters for MySQL, okay. We have areas like, you know, file handles, initial connection requests, ephemeral port and time wait, as well as network buffer size. All those, okay, we actually publish the recommended Linux kernel parameter in our document. Okay, if you run MySQL running on top of virtualization, okay, try to size MySQL VM CPU as a divisor of a NUMA node, okay? Let's say the architecture is supporting NUMA, then try to make sure that the VM CPU is a divisor of NUMA node. And try to size the RAM or InnoDB buffer pool size as a divisor of NUMA node as well. Okay, otherwise, okay, if you cannot do that, okay, check first whether your servers actually is NUMA, having a NUMA architecture. By running either the message or NUMA CTL or cat boot config blah blah blah. Okay, if you see that NUMA is applicable, then please enable InnoDB NUMA interleave by setting InnoDB NUMA interleave to on. But in MySQL 8.4, as my colleague Sumi said this morning, okay, info this morning, that 8.4, by default, InnoDB NUMA interleave is on. Unless you are doing the installing the MySQL below 8.4, it is off. So you need to check the NUMA configuration. If it is on, then set InnoDB NUMA interleave to on as well. And then, last but not least in this page, which is maybe it is good if we also do you know, CPU core affinity. Okay, so that MySQL database servers that are running on VM, the VM vCPU will tied with the CPU core. Okay. And then this is not estimating, this is guesstimating. Why guesstimating? Because no one knows, okay, what is the exact, you know, database sizing applicable for particular workload that never be installed, okay? In this scenario, somebody from the application team or from architecture team, okay, comes to us, okay, as a DBA, okay, can you size my workload? Okay, what typical, what could be the, you know, server size, CPU, RAM? We don't know, okay? We don't know, but we need to come up with some answer, and we need to come up with some baseline. Otherwise, we also don't know unless we test that workload. So we sometimes, we always start with the usual basic question on that. First, what is the number of concurrent users, okay? And then ratio of OLTP versus reporting. And what application that going to run, okay? And then projected data growth and performance SLA in query response time, yeah? And then let's say we have a scenario like, you know, the workload is going to be having 800 concurrent users with OLTP plus 50% reporting on top of that. And then the system need to have 30% of CPU utilization most of the time, 60% RAM utilization most of the time, and 2 to 4 second query response time. So again, this is not available in anywhere. I do some testings, my own testing using OCI Compute Node, that one CPU core is around 400 to 500 transactions per second. So let's say if we have 800 concurrent users, and then we imagine that 800 concurrent users doing a transaction together. So we have 800 on TPS, right? So 800 TPS divided by 400, again, this is guesstimation. Okay, guesstimation. We need to come up with something, okay, to do server sizings, right? It's equal to 2 vCPU. And then based on the requirement, it has 50% of reporting user. So we multiply by 150%, we got 3 vCPU. And then look at the requirement, 30% CPU utilization most of the time. Then times 3, become 9 vCPU. And don't forget that OS also need the vCPU, right? So make it as 12. And then for RAM size, we do like, 1 vCPU equal to 8 gigabyte of RAM. So 12 vCPU times 8 is about 96 gigabyte of RAM. And then we check that memory utilization, it will be like about 60% most of the time. So that's why we cannot use, assume that MySQL can use 96 gigabyte of RAM. Then we can assume that MySQL maximum is 64 gigabyte of RAM. So that when we configure InnoDB buffer pool size, then we know what numbers we need to work on, okay? So with quick estimation on MySQL configuration based on 12 vCPU, 64 gigabyte RAM, and let's say we have, good disk, about 5,000 I/O per second, let's say. First, we can configure the buffer pool size and related variables, like InnoDB buffer pool size is 80% of given memory to MySQL, which is 64 gigabyte times 80%. Okay, we give it 48%. And then InnoDB buffer pool instances. Okay, this morning my colleague Sumi has already said, also said that. Okay, if the buffer pool instances is too small, while buffer pool size is big, then sometimes performance can get, not optimum. Okay, we need to make sure that performance is optimum. So let's say we have, we can create each of buffer pool instances having 2 gigabyte. Therefore, if buffer pool size is 48 gigabyte, then we need to have 24 buffer pool instances. So 24 times 2 gigabyte is 48. And then InnoDB adaptive hash index. If you use 8.4, it's already off. If you use MySQL version below 8.4, it is still on. Then depending on the workload, okay, you might conduct the benchmarking, right? But my suggestion is keep it off. Why? The adaptive hash index is very useful if your application is intensively doing read rather than write. But every write that changes the buffer pool, it will change the content of adaptive hash index. So it is going to be like additional overhead to the MySQL. So suggestion is to keep it off. Okay, do benchmarking. If you want to, out of curiosity, okay, how about if we put it as on, then do some benchmarking? Yes, that's a good way. And then we need to configure buffer pool prefetch, or we call it as read ahead, which is in one I/O, MySQL I/O operation. MySQL will fetch the whole entire pages, okay, from the disk into the buffer pool, one extent, yeah, into the buffer pool. So this is going to be like, reducing the I/O operations while getting more data immediately available in buffer pool instances, buffer pool in the memory, okay, within a single I/O operation. There are two, okay, linear and random. For linear, it's like, if let's say you set InnoDB buffer pool read ahead equal to 13, meaning that in one extent, MySQL reading 13 data, 13 blocks, 13 pages, in sequential, then MySQL will decide, okay, I will load all the pages within that extent to the buffer pool. So that's why it is like predicting, yeah. So it is very workload dependent, okay. But it is good if we can, check if, okay, let's say maybe I want to use default or I want to change the default, okay, and then do benchmarking after that. And then InnoDB buffer pool read ahead random, meaning that I don't have to, if we set if I set this to 13, okay, it doesn't mean that, no, it does not need to be like, in sequence. As long as MySQL read the pages on the disk, okay, 13, okay, in random, then the whole entire extent will be, fetched and put it into buffer pool in one I/O. That one is fetching. How about flushing? Okay, flushing, okay, InnoDB page cleaners. Okay, best practice is to keep it the same as InnoDB buffer pool instances. We have a buffer pool size, and then divide into multiple instances, and then we assign each of instances into one. We assign one InnoDB page cleaners into each instances. Okay, that's how we actually remember. Okay, to always set InnoDB page cleaner to get the same as InnoDB buffer pool instances. And then InnoDB flush networks. This is depending on the disk that you are using. If you are using SSD, okay, to spread across read and write evenly, then just keep it default as 0. Otherwise, if you use a rotational disk, maybe it is good if you check if you can, either 1 or 2. Okay, setting as 1, meaning that, okay, any dirty buffer in a buffer pool, okay, it will flush the whole entire extent in the buffer pool to the disk, if there is any sequential. 2, meaning that there is a random, then the whole entire extent, one extent in buffer pools will be flushed to the disk. And then InnoDB flush method in MySQL 8.4, default is all direct. Before MySQL 8.4, default is fsync. Okay, so yeah, please test. Okay, which one is faster in your setup? Whether you are using fsync, or you are using all direct, or even if you set all direct, no fsync. Okay. But if you are using fsync, then maybe you can instruct MySQL to use fdatasync instead of just fsync. Using fdatasync, okay, whenever MySQL write into the disk, right, into the data files, so it won't update the file metadata. Okay, it's already explained this morning as well. And InnoDB I/O capacity and capacity max set it to 5,000 because we have 5,000 I/O per second. And then LRU scan depth is actually a variable that controls how big is the work of each of the page cleaner. So that's why, since we have InnoDB max capacity is 5,000 I/O per second, so per page cleaner is very simple. 5,000 divided by 24 is around 256. Quick optimization on MySQL InnoDB cluster. So the InnoDB cluster consists of multiple this is a shared netting architecture, consists of multiple database nodes. Okay, minimum nodes is 3, maximum nodes is 9. So always work with the odd number because odd number will give, will easily give the so-called, if there is any problems, right? There is so-called a majority. Yeah. If we have even number, let's say 4, okay, sometimes if 2 is down, then the other 2 will not working because even it does not give the majority. So usually in InnoDB clusters, we have a simple setup. We only have application connect to MySQL router. Application and MySQL router, okay, MySQL router can run on application server, or we can run MySQL routers on separate VM. Okay, but they are connecting on the same LAN, which is application LAN. And InnoDB clusters connecting to DB LAN, and DB LAN to application LAN, there is a interlink over there. So usually by simple setup, all the networks have traffic happening on one DB LAN over here, which is data from the application, from the MySQL routers, as well as the messages communication between the InnoDB cluster, because InnoDB cluster require network to communicate to each other, okay? As well as if there is any recovery required over there, distributed recovery required, then it will use the same data LAN, okay? So in order to have better performance and stability, it is suggested to split, okay, the network between data LAN and private LAN. I call it as private LAN. The private LAN will be used for group replication communication between members by setting group replication local address to IP address that actually, or subnet that used by the second subnet that available over here. And used for setting this new LAN for distributed recovery. Let's say one of the nodes down, and once it is up, it is doing the distributed recovery. Then it will use this LAN, private LAN, instead of the data LAN. Okay, so that the network performance between MySQL routers and database will not get affected. Okay. And this is the InnoDB cluster configuration for performance and reliability. First, we set a group replication paxos single leader if we have a single primary mode, meaning that in InnoDB cluster 3 node, we have one become primary and the other two become secondary. Primary will be running on read-write, secondary will be running on read-only. By setting the group replication paxos single leader equal to on, meaning that the consensus is driven only by primary. So that's networks communication will be less, and then the messaging will be less between the InnoDB cluster member and so on. So that we can relieve some CPU cycle over there. And double up CPU sizing and set parallel worker to equal to original CPU sizing. Meaning that if you size your application as 8 vCPU, 64 GB RAM, maybe it is better if you size up the CPU to 16 GB RAM, okay? And then put replica parallel worker equal to 8. Why? Because many we see that, in replication, we're always dealing with replication lag. And I never see, the slave, almost never see a slave or replicas that actually have, replication lag equal to 0 in busy system. Therefore, we need to, I think we need to double up the CPU sizing and set the parallel worker equal to original CPU size. And then, if we have replication lag, right? Since InnoDB cluster working as a team, as a group, then it will so-called reduce the performance. Why? Because we have a mechanism, what we call it as group replication flow control. Okay, if one secondary node is very lag, then new transaction will be throttled. Okay, and then the whole entire performance will get dropped. So there are two ways how to do it. First, we need to control the so-called the flow controls. We need to fine-tune the flow control so that if there is any lagging, severely lagging on the secondary node, then it won't so-called, it still allow performance to be manageable. Or suddenly just disable the flow control. I've seen in some POC, the InnoDB clusters works like, because the performance was a key. So the InnoDB cluster performed quite well. It's about 1,200 TPS. Okay, but after we check from the tools, it's always dropping, something like this. So it's always high and always dropping. Why dropping? It's because flow control. Then we try to disable the flow control. Okay, set the flow control to disable. Then what happened is the transaction, TPS, jumped from 1,200 into 9,000. And then when we check on the graph, performance graph, it's always like this. Okay, never go down. That means flow control and the CPU sizing is very, very important and related to the performance. And then group replication compression threshold is 1 million, meaning that 1 gigabyte. Then InnoDB cluster 1,000 kilobyte, 1 megabyte. 1 megabyte, then InnoDB cluster will actually compress the data to send the messages to communicate between members. But the idea over here is, okay, let the CPU works a little bit harder to compress the messages if the messages more than 100 bytes and send over to the network so that the networks will get so-called more low traffic. And then we need to set group replication pulse spin loop. Okay, default is 0. Okay, set it to 100 times. 0 means it's always waiting. So until, before it is listening to the next network messages. So by setting to 100, so it will just wait for 100 times. The numbers of group communication thread will wait for releasing the for mutex to be released before listening to the incoming network messages. So it will increase the throughput of the InnoDB cluster itself. And then this, last but not least, okay, in order to make operation easy, okay, for application developers, for DBA, doesn't need to create a primary keys, okay, because the primary keys is so-called mandatory requirement. Okay, if you want to create a tables in InnoDB cluster, primary key is mandatory requirement. But we know that details does not have primary keys. Header, yes, detail does not have primary keys. So we have invisible primary keys. And then we can set this SQL generate invisible primary key equal to 1. So whoever actually create a table without primary keys, it will actually, create invisible primary keys on the back. So MySQL Enterprise Thread Pools. The Enterprise Thread Pools is actually only available in Enterprise Editions. It's actually to, it's not throttling the transactions, but it is, spread out the transaction into a thread pool channel, and then give the allocated RAM and CPU to the thread pool instead of directly goes to the connection thread. Let's say if you have 8,000 connection threads all together going into the MySQL and executing query together, what happened? MySQL need to assign, let's say you only have 8 CPU, then the 8 CPU will be like, getting all the 8,000 at one time. And then it needs to give the memory to the connection as well. There will be a lot of context switching. There will be a lot of memory utilization. So with thread pools, everything can be regulated. So this is the performance after we do thread pools. Okay, after certain concurrent threads, concurrent users, without thread pool it will go down. With thread pool, it will still be able to maintain high performance. Tuning MySQL thread pool for performance, we need to have a baseline for our starting point. It doesn't mean that this is the solution. Moving forward, you always like this. Okay, but again, this is for day one operation. So we need to have one standard. So set the thread pool size equal to physical core. Maximum is 512. Set thread pool maximum transaction limit equal to physical core times 32, maximum 512. Thread pool algorithm set to 1, okay, so for aggressive thread pooling. And thread pool query worker threads per group equal to 2. Why 2? Because this one, we need to have a 2 thread per 1 vCPU, as per Linux standard, right? And then thread pool set it to the vCPU, right? And then thread pool to max transaction limit, yes, times 32, meaning that one thread pool will maximum handle 32. But if you have a 32 virtual CPU, then 32 times 32 is more than 512. Therefore, it will maximum 512. How about if I have huge CPU, I want to use a thread pool? Do I have my thread pooling capped into the 512? Not really, okay, because we can set maximum transaction limit to the same as max connections, so that it will remove the limitation actually. Okay, so these thread pools, as you see on the graph previously, it will provide substantial protections against performance degradation for MySQL Server. Okay, this is a summary. First, hardware sizing and capacity determine upper limit for MySQL. Once you decide, I want to buy 32 core CPU, 128 gigabyte RAM, not enough. What do you want to do? You cannot do anything. You need to buy new hardware. And how about the existing hardware? Okay, cannot. So sizing is always very, very important. But alternatively, you can use a cloud-based implementation because cloud provides elasticity for infrastructure at scale. Day one system setup is very important to lay the foundation for long-term MySQL database performance and reliability. And next, for day two onwards, okay, performance schema is our friend to monitor MySQL internal, okay, if there is any deadlock, bottleneck, whatever it is, and provide information to identify bottleneck, okay, so that we can troubleshoot, okay, during day two operation. Thank you.